Alrighty, so we need to know how to calculate what's known as the root mean square speed, the RMS speed. So with a gas sample, it'd be very tricky and practically impossible to calculate the average speed. Think about how you get averages. You add up, we'd have to know all the speeds of all the particles and then divide by the total number of particles. It would be over the top. It would take forever. So scientists have derived this particular equation from the relationship between kinetic energy and temperature. And it works pretty well. The value that you get when you do a root mean squared speed is pretty close, a little bit bigger usually than the average speed, but pretty close. So it's a very good approximation, and it's how it's done. One thing is that you want to make sure you're using the correct R value here. So I know we're in the gas law section, and all the R values are known as universal gas constants, but there's so many different ones out there. For this particular equation, you want to use 8.314. There's more digits, but 4 is fine for us. 8.314 joules divided by moles times Kelvin. However, we're looking for a speed at the end of the day. So we want our units to make sense and match up. So remember, joules is equal to kilograms times meters squared over seconds squared. So when I use R in this particular equation, I'm going to use the substituted version. So I'm going to do kilograms times meters squared divided by seconds squared times moles times Kelvin. So that's what I'm going to use when we go through these examples, and you should use it too. Temperature, and once you get your R right, everything else kind of falls into place. We know our temperature should be in Kelvin, and that's what this T is. And then this script M down here stands for the molar mass of the gas. It's the same molar mass that we've been doing since day one using the periodic table. The only caveat here is, again, looking at these units, we're going to need to get rid of kilograms and moles. So the units here should be kilograms per mole. Alrighty, so let's jump into some of these problems. Alrighty, so in this first problem, we're asked to calculate the root mean squared speed of gaseous hydrochloric acid at 25 degrees Celsius. Now, you might be thinking, 25 degrees Celsius, that's just a little bit warmer than room temperature. Hydrochloric acid isn't a gas at room temperature, and you're right. But remember that all liquids vaporize to some extent at all different temperatures, right? They start to boil when their partial pressure equals the atmospheric pressure, but for instance, water vaporizes even on a cold day, right? A puddle will eventually disappear. So this is what we're seeing here, some, hydrochloric acid vapor. Trust me, I know from experience that it happens, because when you open up a bottle of pure hydrochloric acid and you're standing too close to it, you definitely get a whiff of it. So what I did, I calculated the molar mass using the periodic table and then converted that to kilograms per mole, so that I have the appropriate molar mass, which went in the denominator of my calculation. In the top, nothing too fancy, 3 times the R value times the temperature in Kelvin. Let's see how everything's canceling. So kilograms will cancel kilograms, moles with moles, Kelvin with Kelvin. And at this point, I'm left with meters squared over seconds squared. So if I multiply and divide, I'll do it in 2 steps, just in case you want to verify your numbers here. I got, still inside the square root house, I got 2.039568 times 10 to the 5th meters squared over seconds squared. Remember, when you take the square root, this is going to become meters per second. So after I did that, I got 452 meters per second. So now would be a good time to very briefly discuss the relationship between root mean square speed, RMS speed, and molar mass. So the molar mass always goes on the bottom, right? So as molar mass increases, root mean square speed will decrease. And that kind of makes sense, right? Let me write it down real quick. So as we increase molar mass, we're going to see a decrease in the RMS speed. I mean, if I'm placing bets on a race, and I'm not trying to be offensive to anybody, but you know, if it's between a very, very large person and maybe a smaller person, I kind of would think that the smaller person would get to the finish line faster. Hey, you never know, right? Sometimes things shock you, but typically, like, you know, the smaller something is, the faster it can move. Even if we look at children, right? They're insanely fast and they're hyper all the time, and they're very, very small. So once again, the take home from this one is, as we increase molar mass, we're going to decrease the RMS speed. On this last problem, we're asked to compare the RMS speeds of nitrogen gas in the summer and in the winter. Very interesting, very applicable to day-to-day life. The majority of our atmosphere does consist of nitrogen gas. Just think about all those gas molecules that you can't see and what they're doing. So for the summer day, I took the 37 degrees Celsius and converted it to Kelvin. I got 310.15 Kelvin. In addition, I calculated the molar mass of N2, around 28 grams per mole, and then I divided it by 1,000 because it has to be kilograms per mole when you plug it in. So looking at all these units canceling just one more time, kilograms with kilograms, moles with moles, Kelvin with Kelvin, we're left with meters squared over seconds squared. But when we take the square root of our numerical value here, that's going to go to meters per second. So on that summer day, we have a root mean squared speed for the nitrogen of 525 meters per second. I redid the problem for the winter when the temperature was quite a bit colder, right? That's insane. I don't want to go back there. Anyways, so that converted to 248.15 Kelvin, dividing by the same molar mass, and I got a speed of 470 meters per second. So this helps highlight another relationship, but you've always known this relationship since you started chemistry. And that's the idea that as temperature increases, the speed at which the molecules are moving also increases. So if we see an increase in temperature, we're going to see an increase in the speed.